Hello, and welcome to Cardiff Science Festival for those that this is their first talk. So we got a lot of exciting things on for the rest of today and tomorrow, and you can still book tickets online, just to say. And here I am going to be talking to everyone about symmetry. So a little bit about myself. I'm a doctoral student at the Uni of Glasgow in mathematics, which means that I think about maths for my job. But I'm doing it remotely at the moment. So I live in Cardiff, so I've been able to catch a little bit of Cardiff Science Festival. And I did my sort of undergraduate degree in Cardiff University as well. So that's why I'm here, despite being a Uni of Glasgow student. And I'm here talking about something which I think a lot of people are interested in, which is symmetry. So, but specifically, I'm talking about how symmetry finds its way into science. So when I think of symmetry, and when a lot of people think of symmetry, we think of different things. So for a lot of people, symmetry sort of conjures up pictures of snowflakes, of isosceles triangles in school, and this kind of thing. And it's a very strong part of primary school mathematics. And then by secondary school, it's sort of off the syllabus, really. But we learned quite a few key things. So we learned what a symmetry is in primary school. So a symmetry is when you perform some sort of transformation, so like a rotation or a reflection, and it leaves it exactly how it was before. So if I reflect along any of these dotted lines, I'll get the same triangle as I did before. We also sort of identify different shapes by what kind of symmetries they have. So, as I said before, an isosceles triangle would have one line of symmetries, where like an equilateral triangle will have three lines. So there's these sort of classifications coming from symmetry. But when I'm thinking of symmetry, I think of something called group theory. And group theory is sort of the way that modern mathematicians talk about symmetry. It relates to symmetry in the same way as algebra relates to questions about numbers. So in the way in which at some point we started thinking of numbers as x and y, we started thinking of symmetries as A or A inverse, and trying to make equations out of different types of symmetry. So I wanted to start off by telling you a little bit about the history of it, because I think the history of group theory is really interesting. So the first people that really sort of dedicated their lives to studying symmetry would have been in the Ottoman Empire. So I put there on a date of around about 825 Common Era. So it would have been Islamic scholars that were studying symmetry for sort of religious reasons. At the time, symmetry was a really important sort of pillar of Islam. And anyone who knows a bit about the history of maths in this sort of era, this was sort of the center of mathematics, was what we'd now call Iraq. And people were making huge strides towards notational things. So people were using equal signs for the first time, or people were establishing sort of for the first time algebra and this kind of thing. And some people had started to try and people had started to try to classify different types of symmetries already by this sort of time, by looking at different types of shapes. And people had started to define isosceles, triangles, and this kind of thing. Now, this was sort of where it all began, but it's changed a lot in modern times. So now people that think about symmetries are looking at things like this. So we've got a few strange pictures here, which are all sort of representing different things. So in modern group theory, we have all kinds of symbols and sort of algebras and equations that help us to understand essentially underlying symmetries. But one of the most important ones that we have is this concept of a group. Now, what a group is the set of all the transformations that you can do to a certain object. It's as simple as that. And what this has is a sort of way of making equations and symbols out of this symmetry, which is like incredibly useful. And this is what's called group theory. By the mid-19th century, group theory was really up and running. So people had defined what a group is. People had understood well that for every object, there's a group, and for every group, there's an object. And since then, all kinds of progress has been made. So the biggest sort of mark of progression in modern group theory is the classification of finite simple groups. This is a huge result in mathematics. Arguably, it's the biggest result ever to come out of mathematics. So what it essentially is what are the building blocks of groups? It's like we've managed to write the periodic table of elements, but for groups. And this result took over 100 years of like directed effort by, I'd say, thousands of different mathematicians. And we've got more than 10,000 pages of papers, which is really huge for a result in mathematics. Most theorems take about 30 pages to prove, maybe 40 pages. 10,000 pages is really insane. I mean, it's much, much longer than the Bible. So despite us making huge strides towards this, there's all kinds of things that we don't know about symmetries. And I think this is quite an intriguing thing to a lot of people. And essentially what this comes down to is that there's all kinds of objects that can be very strange. So here what we've got is a tesseract in the bottom right-hand corner, which is a sort of 4-dimensional shape. And this has all kinds of strange symmetries, which we don't see in sort of 3 dimensions or have the same sort of intuitions towards as we have in 3 dimensions. We've also got sort of this strange surfacey thing in the top left-hand corner, which is sort of like, again, something that evolves throughout time. It's sort of almost like scanning the surface of an object. And so you get these sort of like partial symmetries coming up as well. Essentially, there's all kinds of different groups and there's infinite groups. So we've still got a lot of work to go, which is good because otherwise I would be out of a job. So why is it so hard? Why is symmetry a hard thing to understand? And the example that I'm gonna give to people is that of a Rubik's Cube. Um, so this might be a bit of a strange thing to imagine as a symmetry, but if you imagine my Rubik's Cube over here, it's just colored in completely black, doesn't have any stickers on it. Then when I go like this, we can think of this as a symmetry, right? Because it's a transformation which leaves the underlying shape exactly the same as it was before. But what this sort of does is keep track of what move I've just done. That's sort of what the stickers are for. And so it keeps track of all the different types of symmetries. So there's 6 sort of fundamental moves that one can do. One can go like this. One can go like this. Like this. Like this. Or rotate like that. Or rotate like that. And every other sort of move you can do as some sort of sequence of these moves. So it's generated by these 6 moves. But as we see, we've got a very big number in the bottom left-hand corner, and the number of combinations of one of these Rubik's Cubes could have is more than 43 trillion. So if we had sort of one Rubik's Cube for every different sort of set of colors that we could have, that would be enough to cover the world 275 times over. So a group, even that's generated by a very small number of sort of things, which we understand, has this sort of almost random quality to it that's very hard to like compute things with. That said, people do know how to solve Rubik's Cubes. So this is the sort of strength of group theory, is that it turns all of these strange equations into this nice set of rules, which people can then sort of work things out about in reality. So that's sort of the half of my talk, which is on the sort of like more abstract side of group theory and the more mathematical side. And now I'm going to sort of turn my attention to the question of why is it useful? So we've got that lots of people are interested in all kinds of types of groups, all kinds of types of symmetry. And now we want to turn to, so why are people interested in it from a perspective of science? So the first one that I would like to talk about is, I see we've got some interest from Paul about physics, so he'll be happy to see that we're into physics. I'll answer your question at the end, Paul. So the first sort of area of science that I wanted to talk about was sort of theoretical physics. Now, it's not a sort of understatement to say that every sort of conservation law arises naturally as some type of symmetry. So we see here a GIF describing some sort of conservation law. So we've got this sort of independent motion of these two point masses, and you see that they are falling at the same rate despite having different sort of vertical velocities. And this is sort of quite a well-known thing within physics, but it should be quite intuitive, I think, to people that this involves some kind of symmetry. And it makes a lot of physics a lot more simple. It would probably be overkill in classical mechanics, so looking at these things like point masses, to actually involve group theory in them. Where it really comes in useful is when we're looking at very, very small objects. So I've got this picture of an atom here, and then I've got this very strange looking equation in the bottom left-hand corner, and this is called the Schrödinger equation. And it's one of the most important equations in quantum physics. It's essentially like F equals ma for the sort of quantum world. So what has symmetry got to do with this? Well, much in the way as we have above, it really helps us to simplify this equation to understand all of its symmetry. So this Schrödinger equation, for those who know what they're looking at, will have all kinds of different solutions. And it turns out that what is interesting about all of these solutions is that they have very interesting symmetries. So in a way, what we're looking at is what sort of behavior does all of the solutions have, rather than just looking for one solution. It's very different to sort of usual, I guess, usual classical mechanics. So it's very important in physics. It's very important in sort of string theory and quantum physics. And anyone who's seriously interested in these things needs to learn a little bit of group theory. Now that's a little bit sort of science fiction-y and very theoretical. So I just wanted to bring it a little bit down to earth and talk about chemistry. So chemistry has a lot of applications in symmetry, or symmetry has a lot of applications in chemistry. So an important thing to notice is, much like how we describe different types of triangles and different types of shapes, we can describe different chemicals by what's called their symmetry point group, by what different symmetries they have. And this is a really concrete way that helps us every day to identify different chemicals. So in modern times, people identify chemicals a lot of the time through a technique called NMR spectroscopy. And what this does is sort of vibrate the chemicals a bit and see what different symmetries they have. And using this, you obtain a very accurate picture of the chemical makeup of whatever you've put into your NMR spectroscoper. So this helps us to understand what chemicals are in our medicines, what chemicals is in the water, things like this, which is incredibly important. So my partner works in chemistry, and they use an NMR spectrometer nearly every day in work, and underlying this is group theory. Another very concrete one is to talk about viruses and symmetry. So I'm sure we're all quite tired of seeing this particular picture of a coronavirus, but I'm sure that no one doubts the importance of understanding such viruses. And actually, one technique that we use to understand viruses is by looking at their symmetries. So specifically, we're talking here about viruses like coronavirus, which are formed out of a sort of sphere with these sticky bits coming out of it. And these sticky bits are called attachment proteins. So what is important for this is that different viruses will have these attachment proteins coming out in different places, and these attachment proteins are what attaches to our cells and attacks us if we get infected with a certain virus. So the number of these attachment proteins is incredibly important. It corresponds to things like its transmissibility. And so understanding how many of these we have is very important. But we can't take a 3D image of a virus most of the time. We can only take a 2D image. And so we almost have like the shadow of viruses. And so it's very hard to get a picture of what the whole 3D object would look like. And that's where group theory comes in, because you can understand the symmetry of different sort of snapshots. Think of it like a shadow puppet of a virus. And then from that, work out what virus it actually is. So this is one of the methods that people classify viruses through symmetry. It's also what we use to classify new variants of coronavirus. So when the symmetry is sort of different enough, this corresponds to a new variant. And then a final thing that I wanted to touch upon, I know it's Cardiff Science Festival, so we obviously are mainly interested in the science of everything, but symmetry has this inherent beauty to it. It's used in architecture, music, art, and it has this sort of fundamental attraction by a lot of people towards it. So symmetry, we have beautiful mandalas, we have wallpapers, and all of these correspond to groups. In music, we have scales which will sort of go A, B, C, D, E, F, G, A, B, C, D, E, F, G, which corresponds to the similar group to a clock, which goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 2, 3, 4. And you have all of these beautiful connections between sort of our aesthetics as well coming into things. In architecture, intuitive building design often uses group theory. And this led Ian Stewart, who's a very prominent group theorist in the UK, to say that group theory is the study of beauty. And I'd say that a lot of mathematicians, their interest towards group theory lies in how beautiful it can be, just as much as how useful it can be in chemistry, in viruses, in physics. So I just wanted to say now, thanks for listening, and thanks a lot to Cardiff Science Festival for letting me speak on this amazing platform. Thanks to Uni of Glasgow for letting me sort of have this time to prepare this talk. And I've got here some things for people if they're interested in certain things that came up in talk. So I've got here Why Beauty is Truth, The History of Symmetry by Ian Stewart. So this is a great sort of historical analysis of group theory, and talks all about interesting applications to science. We have this Richard Ellis article called An Enormous Theorem, Classification of Finite Simple Groups, and this explains a bit more of the achievement that was made from this tremendously large theorem, the classification of finite simple groups. And then a bit of a sort of softer recommendation that I think is a really beautiful book is this book, Beautiful Symmetry, a colouring book about maths. So it's a sort of like a usual colouring book, but every picture has some relevance to group theory. So it's just like a really nice way to learn about that sort of area of maths in a sort of like nice, mindful, maybe slightly artistic way. And then I've got sort of some shameless QR code plugs for my blog. Talks just a bit about what it's like to study mathematics and what it's like to be a mathematician. And a newspaper piece that I wrote for the Glasgow Institute of Science and Technology about symmetry. So that's on the left-hand side and the right-hand side. And yeah, as said, if anyone has any questions, I'm more than happy to answer them now. So I'm going to head over to the Cardiff Science Festival slide, which I was... So I can see there's already a few questions in the chat, but just feel free to comment if you have any more questions. So a first question from Paul Nugent. How can symmetry and order exist in an entropic universe that tends to chaos? I think this is an interesting question. What I would say is that, first of all, chaotic behavior sometimes has certain symmetrical things. So if I was to jumble this up, this would look very chaotic. And I think this is what I was sort of getting at in the slide about sort of Rubik's cubes, is that despite following some very rigid rules, groups give us sort of actually quite chaotic and strange behavior that we don't really understand. Then sort of what this helps us model is chaos or chaotic different things, or it helps us understand, okay, so yes, we have a sort of more quantum understanding of the world. So this is what was going on a bit with the Schrödinger equation. Yes, we have all kinds of different possibilities for what might happen and sort of chaotic things. But what do these things have in common? And usually groups hold the answer to sort of what these things have in common, and what do we have together. So then next question from JJ Klum. So how does the vibration reveal symmetry in an NMR spectroscope? So yeah, sorry if I wasn't clear about this one. So if one has a shape like this, then the NMR spectroscopy machine will sort of go like shuffling around like that. But every time it is sort of back to the space where it was before, so it's vibrating all around, but every time it's in the space where it was before, it sort of takes note of that, and that's the way it works, basically. So on to the next question. I'll try and get everyone's question done. So Kavitha, how is symmetry used in space? Yeah, so this is something that I didn't have time to talk about, but symmetry is also used to study sort of large objects as well, like in astrophysics and stuff like that. We have all kinds of sort of some of the most symmetrical things are things like circles and spheres and things like that, which happen a lot in astrophysics. So the orbits of different planets and this sort of thing. And that is very essential to understand sort of group theory in order to understand the placement of different objects and things like this. And then, yeah, and then another question from Paul. So is chaos symmetry we don't understand yet? And a reply by Ulrich, who's a lecturer at Cardiff University. So yeah, that's a good answer by Ulrich. So it's not that chaos is symmetry we don't understand, but it's that the only way that we can understand chaos is through its symmetry. So we can't necessarily say exactly what's going to happen to an object, but we might be able to say that there's some sort of symmetry to all of the things that could happen with it. So yeah, that's well answered by Ulrich as well. Okay, we're just about running out of time. So thank you so much again to Cardiff Science Festival and to the Uni of Glasgow. And yeah, if you enjoyed my talk and you know someone that wasn't able to come, I'm also speaking tomorrow at 2 p.m. And thanks a lot for listening. Okay.